Langchain OpenAI chat models. Description: explain in detail. Langchain OpenAI chat models are a powerful way to integrate OpenAI's large language models (LLMs) into your applications. They offer a flexible and user-friendly interface for interacting with these models, allowing you to perform various tasks like text generation, translation, summarization, and more. These models are built upon the OpenAI API and are accessed through the Langchain framework. Inputs. Input 1. Explain in detail. Prompt: the user's input that serves as a starting point for the LLM. This can be a question, a statement, a task description, or any text that you want the model to process. Input 2. Explain in detail. Context. You can provide additional context to the model beyond the initial prompt. This can be in the form of previous conversation history, relevant documents, or any other information that could help the model understand the task better. Outputs. Output 1. Explain in detail. Text response. The LLM generates a text output based on the prompt and context provided. This could be a direct answer to a question, a creative text snippet, or any other type of text. Output 2. Explain in detail. Structured output. Depending on the task and model configuration, the LLM may produce structured outputs like lists, tables, or JSON objects. This is useful for extracting specific information or for tasks requiring a more organized format. Steps. Step 1. Explain in detail. Prompt construction. You craft a prompt that effectively communicates the desired task to the LLM. This requires understanding the model's capabilities and limitations. Step 2. Explain in detail. Model selection. Choose the appropriate OpenAI LLM from Langchain's library based on your task requirements. Different models specialize in different areas, e.g., text generation, translation, code completion. Step 3. Explain in detail. Context integration. If necessary, you provide relevant context to the model through Langchain's mechanisms, such as using a chain to process prior conversation history or load related documents. Step 4. Explain in detail. Execution. Langchain handles the interaction with the OpenAI API, sending the prompt and context to the selected LLM. Step 5. Explain in detail. Response processing. Langchain receives the LLM's output and may perform additional processing based on the task requirements, such as extracting information or formatting the response. Metrics. Metric 1. Explain in detail. Accuracy. How well the model's response aligns with the intended outcome or correct answer, especially for tasks like question answering. Metric 2. Explain in detail. Fluency. The readability and naturalness of the generated text. This is crucial for tasks like creative writing or text summarization. Metric 3. Explain in detail. Relevance. How well the generated text relates to the provided prompt and context. Visualization plots. Visualization plot 1. Explain in detail. Prompt effectiveness plot. Analyze different prompt variations to identify which prompts yield the best results for a specific task. Visualization plot 2. Explain in detail. Model performance comparison. Compare the performance of different OpenAI LLMs for a given task to determine which model is most suitable. Visualization plot 3. Explain in detail. Response analysis. Visualize the model's outputs over time to identify patterns or trends, especially in tasks like sentiment analysis or topic extraction. Fine-tune parameters. Parameter 1. Explain in detail. Temperature controls the randomness of the model's output. Higher temperature values lead to more creative and surprising outputs, while lower values produce more predictable and deterministic responses. Parameter 2. Explain in detail. Top K limits the number of possible words considered for each token during generation. This helps to control the model's output space and can improve the quality of the generated text. Parameter 3. Explain in detail. Top. Similar to top, but instead of limiting the number of words, it limits the probability of the next token based on a threshold. Parameter 4. Explain in detail. Max tokens defines the maximum number of tokens that the model can generate in a single response. Parameter 5. Explain in detail. Frequency penalty. This parameter encourages the model to avoid repeating the same words or phrases excessively, leading to more diverse and interesting outputs. Parameter 6. Explain in detail. Presence penalty penalizes the model for generating words or phrases that have already appeared in the prompt or context, promoting more creative responses. Uncertainty methods. Uncertainty method 1. Explain in detail. Ensemble prediction. Use multiple LLMs or different versions of the same LLM to make predictions. Then combine the results to estimate the uncertainty. Uncertainty method 2. Explain in detail. Confidence scores. Some LLMs provide confidence scores for their generated outputs. This can help assess the reliability of the response. Uncertainty method 3. Explain in detail. Entropy-based uncertainty. Calculate the entropy of a model's output distribution to quantify the uncertainty in the generated response. Challenges and fixes. Challenge 1. Explain in detail. Prompt engineering. Crafting effective prompts that accurately communicate the desired task is crucial. A vague or poorly worded prompt can lead to inaccurate or irrelevant outputs. Specificity. Provide clear and specific instructions in the prompt. Examples include example inputs and expected outputs in the prompt. Structure. Use a structured format to organize the prompt, e.g., question-answer pairs. Challenge 2. Explain in detail. Context management. Handling large amounts of context can be challenging, especially when dealing with long conversations or extensive documents. The model may struggle to remember all the details from a long conversation, leading to inconsistencies or inaccuracies. Chunking. Split large amounts of text into smaller chunks. Summarization. Use techniques to summarize large amounts of text before passing them to the model. Context retrieval. Utilize tools like vector databases to efficiently retrieve relevant context from large datasets. Challenge 3. Explain in detail. Bias and safety. LLMs can exhibit biases or generate unsafe content, reflecting the biases present in their training data. Sample use case that resulted in challenge 3. The model may generate offensive or harmful language, or perpetuate existing societal biases. Fixes to challenge 3. Fine-tuning. Fine-tune the model on a specific domain or dataset to address bias and improve safety. Content moderation. Use tools and techniques to filter out harmful or biased content from the model's output. Human supervision. Human oversight is essential for detecting and correcting biased or unsafe outputs. Challenge 4. Explain in detail. Computational cost. Using large LLMs can be computationally expensive, especially for complex tasks or large input sizes. Sample use case that resulted in challenge 4. Running the model on a large amount of text or with complex prompts can consume significant resources. Fixes to challenge 4. Resource optimization. Use smaller models or optimize parameters for efficiency. Model compression. Utilize techniques like model compression to reduce the size of the model without significantly impacting performance. Efficient execution. Employ methods like batch processing and caching to optimize the execution of the model. Langchain Open AI chat models. Azure Chat Open AI. Description. Azure Chat Open AI is a Langchain integration for using OpenAI's ChatGPT models deployed on Azure OpenAI service. It leverages the capabilities of Azure OpenAI service to provide secure, scalable, and reliable access to advanced language models. Inputs. Model name: the name of the OpenAI model to be used. This can be a GPT-3 model like Text DaVinci 003 or a ChatGPT model like GPT 3.5 Turbo or GPT-4. Temperature controls the randomness of the generated text. Higher values, e.g., 1, lead to more creative and unpredictable outputs, while lower values, e.g., 0, produce more deterministic and consistent responses. Max tokens limits the maximum number of tokens the model can generate in a single response. This helps to control the length of the generated text and prevents excessively long outputs. Top controls the diversity of the generated text. It specifies the probability mass of the most likely tokens to be sampled from. A higher value, e.g., 1, allows for a wider range of tokens, while a lower value, e.g., 0.5, restricts the sampling to more likely tokens. Top. Similar to top, it controls the diversity of the generated text by limiting the number of tokens to be considered. During sampling, a higher value, e.g., 50, allows for a wider range of tokens, while a lower value, e.g., 5, restricts the sampling to a smaller set of tokens. Presence penalty influences the model's tendency to repeat previously generated tokens. A positive value penalizes repetition, leading to more diverse outputs. A negative value encourages repetition, potentially resulting in outputs that focus on specific concepts or phrases. Frequency penalty: similar to presence penalty, it controls the repetition of tokens but considers their overall frequency in the generated text. A positive value penalizes frequently used tokens, promoting diversity, while a negative value encourages their use, potentially leading to repetitive or biased outputs. Stop: a list of strings that, when encountered in the generated text, will cause the model to stop generating further tokens. This is useful for limiting the length of responses or directing the model's output towards specific topics. Outputs. Response: the generated text output from the OpenAI model. This is a string containing the response to the input prompt. Steps. Authentication: the library utilizes Azure OpenAI Service API key for authentication and access to the chosen model. Model selection: the user specifies the desired OpenAI model, e.g., GPT-3.5 Turbo, which is then selected from the available models in Azure OpenAI Service. Prompt input: the user provides a text prompt or question as input to the selected model. API request: Langchain constructs and sends an API request to Azure OpenAI Service containing a prompt, model parameters, and authentication credentials. Response handling: Azure OpenAI Service processes the prompt and generates a text response. The response is then passed and returned by Langchain. Metrics. Latency: the time taken for the model to process the prompt and generate a response. Token consumption: the number of tokens used by the model to generate the response. Model performance: evaluating the quality, accuracy, and fluency of the generated text. Visualization plots. Token usage over time: a plot showing the number of tokens used by the model across multiple requests or over a specific time period. Response time distribution: a histogram representing the distribution of response times for various prompts. Model performance metrics plots visualizing metrics like perplexity, blue score, or rouge score to assess the quality of generated text compared to ground truth or reference data. Fine-tune parameters. Learning rate: the step size used during model training to adjust the model's parameters. Epochs: the number of times the entire training dataset is used to update the model's weights. Batch size, the number of training samples used to compute a single gradient update. Regularization strength, a parameter used to prevent overfitting by adding a penalty to the models. Loss function based on the magnitude of its weights. Uncertainty methods. Temperature sampling, higher temperature values lead to more diverse and uncertain outputs, while lower values result in more deterministic and less uncertain responses. Top K sampling, this method limits the number of tokens considered during sampling, which can reduce uncertainty by focusing on the most likely tokens. Top P sampling, similar to Top K sampling. It controls the probability mass of tokens considered for sampling, influencing the uncertainty level of the generated text. Challenges and fixes. Challenge 1: insufficient token limit causing truncated outputs. Sample use case that resulted in challenge 1: a lengthy prompt or complex request exceeding the default token limit. Fixes to challenge 1. Increase the max tokens parameter to accommodate longer responses. Challenge 2: model responding with generic or irrelevant outputs. Sample use case that resulted in challenge 2: a poorly formulated prompt or ambiguous query, leading to inaccurate or nonsensical responses. Fixes to challenge 2. Improve the prompt structure, providing clear context and specific instructions. Use additional model parameters like temperature or top to control the randomness and diversity of the generated text. Consider using a different model with better capabilities for the specific task. Challenge 3: latency issues due to network congestion or high server load. Sample use case that resulted in challenge 3: a large number of concurrent requests or network issues causing delays in response times. Fixes to challenge 3. Use the Azure OpenAI services scaling options to increase the number of available resources. Implement retry mechanisms in the code to handle temporary network outages. Consider using a caching layer to store frequently accessed responses and reduce the need for repeated API calls. Challenge 4: cost optimization for frequent model usage. Sample use case that resulted in challenge 4: a high volume of requests resulting in significant expenses for Azure OpenAI service. Fixes to challenge 4. Optimize prompts to reduce the number of tokens required. Utilize a caching layer to store and reuse previously generated responses. Consider using a less expensive model for less demanding tasks. Langchain OpenAI chat models. Base chat OpenAI. Description-based chat OpenAI is the foundation for using OpenAI's chat completion API within Langchain. It provides a simple yet powerful interface to interact with the API and generate text responses. Inputs. Prompt: the user's input that serves as the context for the chat conversation. Temperature: a value between 0 and 1, indicating the level of creativity and randomness in the generated response. Lower values produce more predictable and focused responses, while higher values lead to more creative and diverse outputs. Max tokens: an upper limit on the number of tokens that the model can generate in response to the prompt. This helps to control the length of the generated text. Top: a value between 0 and 1, used to control the diversity of the generated text. It specifies the probability distribution of the next token to be generated. Frequency penalty: a value between -2 and 2, which affects how frequently certain words or phrases are used in the generated response. A positive value penalizes the model for using words that have appeared frequently in the input prompt. Presence penalty: a value between -2 and 2, similar to frequency penalty, but focuses on the presence of words or phrases in the generated response. It penalizes the model for using words that have already appeared in the input prompt. Model: the specific OpenAI model to use for generating responses. It is often set to GPT 3.5 Turbo or GPT-4. Outputs. Text: the generated text response from the OpenAI model. Steps. Initialize the base Chat OpenAI class with the desired OpenAI model and API key. Pass the user's input prompt to the call method of the base Chat OpenAI object. The class internally interacts with the OpenAI chat completion API using the provided prompt and configuration parameters. The API processes the prompt and generates text, which is then returned by the call method as the text output. Metrics. Latency: the time taken for the OpenAI model to generate the text response. This can be measured as the difference between the time when the prompt is received and the time when the generated response is returned. Token count: the number of tokens used to generate the response text. This helps to monitor the cost of using the OpenAI API. Visualization plots. Response length distribution: a histogram showing the distribution of the length of generated responses in terms of tokens. Fine-tune parameters. Model: the specific OpenAI model used. Temperature: the level of creativity and randomness. Uncertainty methods. Temperature: higher temperature values introduce more uncertainty and randomness in the generated response. Challenges and fixes. Challenge 1: the OpenAI model may sometimes generate responses that are factually incorrect or contain inappropriate content. Sample use case that resulted in Challenge 1: a prompt asking about the history of a specific event might receive a response with inaccurate information. Fixes to Challenge 1. Double-check the generated responses for factual accuracy and consistency with known information. Use external knowledge sources and fact-checking tools to verify the information provided by a model. Challenge 2: the model's responses can be repetitive or lack creativity. Sample use case that resulted in Challenge 2: a prompt asking for a creative story might receive a response that is predictable and follows common tropes. Fixes to Challenge 2. Increase the temperature parameter to encourage more diverse and less predictable responses. Provide more context and details in the prompt to guide the model towards more creative outputs. Challenge 3: the model might be unable to handle prompts that require reasoning or complex logical thought. Sample use case that resulted in Challenge 3: a prompt asking to solve a logic puzzle might receive a response that is irrelevant or incorrect. Fixes to Challenge 3. Break down complex prompts into smaller, more manageable steps. Use chain techniques to combine multiple smaller models to address complex tasks. Langchain OpenAI chat models base Chat OpenAI. Description: explain in detail the Chat OpenAI class is a base class for interacting with OpenAI's chat models, like GPT 3.5 Turbo and GPT-4. It provides a standardized interface for sending prompts and receiving responses, while allowing for customization of model parameters and other settings. Inputs. Prompt: a string containing the user's prompt. This can be a simple question, a more complex instruction, or a conversation history. Temperature: a float between 0 and 1 that controls the randomness of the model's responses. Higher temperatures lead to more creative and unpredictable outputs, while lower temperatures lead to more deterministic responses. Top: a float between 0 and 1 that controls the probability distribution of the model's responses. Lower values restrict the model to more likely responses, while higher values allow for a wider range of outputs. Top: an integer that controls the number of tokens considered by the model during sampling. Lower values restrict the model to a smaller set of possible responses, while higher values allow for a wider range of outputs. Max tokens: an integer that limits the maximum number of tokens in the model's response. This can be used to control the length of the response. Model name a string representing the specific OpenAI chat model to use. Outputs. Text a string containing the model's response to the prompt. Steps. The chat OpenAI class sends the provided prompt to the specified OpenAI chat model. The model processes the prompt and generates a response. The response is returned to the user. Metrics. Perplexity, a measure of how well the model predicts the next token in a sequence. Lower perplexity indicates a better understanding of the input text. Accuracy, the percentage of correctly answered questions or tasks. Visualization plots. Response length distribution, a histogram showing the frequency of different response lengths. Token frequency, a bar chart showing the frequency of different tokens in the model's responses. Fine-tune parameters. Learning rate controls the step size taken during model training. Batch size, the number of training examples processed at once. Epochs, the number of times the entire training dataset is iterated over. Uncertainty methods. Temperature scaling, adjusting the temperature parameter during inference can provide insights into the model's confidence in its predictions. Ensemble methods, using multiple models to generate responses and then averaging the results can reduce uncertainty. Challenges and fixes. Challenge 1. The model may generate responses that are factually incorrect or biased. Sample use case that resulted in challenge 1. A user asks for a summary of a historical event, and the model provides inaccurate information. Fixes to challenge 1. Use a model that has been fine-tuned on a dataset of factual text. Provide the model with additional context or background information to improve its accuracy. Use a fact-checking tool to verify the model's responses. Challenge 2. The model may generate responses that are repetitive or lack creativity. Sample use case that resulted in challenge 2. A user asks the model to write a poem, and the model produces a poem that is very similar to existing poems. Fixes to challenge 2. Increase the temperature parameter to encourage more randomness in the model's responses. Use a model that has been trained on a dataset of creative text. Provide the model with more specific instructions or prompts to guide its creativity. Challenge 3. The model may generate responses that are offensive or inappropriate. Sample use case that resulted in challenge 3. A user asks the model to tell a joke, and the model generates a joke that is racist or sexist. Fixes to challenge 3. Use a model that has been trained on a dataset of safe and respectful text. Implement content filtering to block offensive or inappropriate responses. Provide the model with clear guidelines on what is acceptable content. Langchain OpenAI embeddings. Description. Langchain OpenAI embeddings are a powerful tool for representing text data as numerical vectors. This allows for efficient comparisons and analysis of text, enabling tasks like text similarity search, clustering, and information retrieval. Inputs. Text. The input text that needs to be converted into an embedding. It can be a single string or a list of strings. Model. The OpenAI embedding model to use for generating embeddings. Common options include text embedding ADA 002. Text similarity DaVinci 001, and text search DaVinci Query 001. Outputs. Embeddings. A list of numerical vectors, where each vector represents the corresponding input text. Steps. Text preprocessing. Input text is cleaned and preprocessed to remove irrelevant characters, punctuation, and stop words. Embedding generation. The preprocessed text is passed to the chosen OpenAI embedding model, which generates a numerical vector representing the text's semantic meaning. Metrics. Cosine similarity measures the similarity between two embedding vectors, with values closer to 1 indicating higher similarity. Euclidean distance measures the distance between two embedding vectors, with smaller values indicating higher similarity. Visualization plots. Tsne reduces the dimensionality of the embedding vectors to 2 or 3 dimensions, allowing visualization of text relationships in a scatter plot. Principal component analysis (PCA) reduces the dimensionality of embedding vectors, highlighting the most significant variations in the data. Fine-tune parameters. Model. Choosing the appropriate embedding model for your task is crucial. Some models are optimized for specific tasks like text similarity, while others excel in information retrieval. Uncertainty methods. Confidence scores. Some embedding models provide confidence scores indicating the model's certainty about the generated embedding. Challenges and fixes. Challenge 1. Choosing the right model. Choosing the appropriate embedding model can be challenging, as different models are optimized for different tasks. Sample use case that resulted in challenge 1: using a text similarity model for an information retrieval task may lead to suboptimal results. Fixes to challenge 1: carefully consider the task at hand and choose a model that aligns with the specific requirements. Experiment with different models to find the best fit for your use case. Challenge 2: handling large text datasets. Processing large datasets can be computationally expensive and may require optimization techniques. Sample use case that resulted in challenge 2: processing a large corpus of documents for text similarity search can consume significant resources. Fixes to challenge 2: implement efficient data loading and processing techniques. Consider using techniques like batch processing to divide the dataset into smaller chunks for processing. Langchain Open AI embeddings. Azure Open AI embeddings. Description. Explain in detail. The Azure Open AI embeddings class provides a way to generate embeddings for text using the OpenAI embedding models, specifically designed for integration with Azure OpenAI service. These embeddings are numerical representations of text, allowing you to compare and analyze text similarity. Inputs. Text: a string containing the text you want to embed. Model optional: the OpenAI embedding model to use, defaulting to text embedding ADA002. You can choose other models like text embedding Curie 001, text embedding Babbage 001, etc. based on your needs. Outputs. Embeddings: a list of floating point numbers representing the embedding of the input text. Steps. The input text is sent to the specified OpenAI embedding model. The model processes the text and generates a numerical representation embedding of it. The generated embeddings are returned as a list of floating point numbers. Metrics. Cosine similarity: this metric is commonly used to measure the similarity between two text embeddings. The closer the cosine similarity is to 1, the more similar the texts are. Visualization plots. Embedding visualization. Embeddings can be visualized in multi-dimensional space using techniques like Tsne or PCA for understanding relationships and clusters among different text samples. Fine-tune parameters. None. You do not fine-tune the OpenAI embedding models themselves. Uncertainty methods. None. OpenAI embedding models are not designed to provide uncertainty estimates. Challenges and fixes. Challenge 1: incorrect model selection. Using an inappropriate embedding model for your task can lead to poor results. Sample use case that resulted in challenge 1: using text embedding ADA002 for long documents might not be ideal due to its limited context window. Fixes to challenge 1: choose a model that is suitable for the length and complexity of your text. For longer documents, consider text embedding Curie 001 or text embedding Babbage 001. Challenge 2. A P key or endpoint issues incorrect or missing a P key or endpoint configuration can prevent successful communication with the Azure OpenAI service. Sample use case that resulted in challenge 2 using an incorrect API key or an invalid endpoint URL. Fixes to challenge 2. Double-check your Azure OpenAI service deployment details. API key and endpoint URL. Ensure they are correct and accessible. Langchain OpenAI embeddings base OpenAI embeddings. Description: the OpenAI embeddings class in Langchain is a powerful tool for generating vector representations of text, enabling semantic search, similarity analysis, and other advanced NLP tasks. It leverages OpenAI's cutting-edge embedding models, like text embedding ADA002, for accurate and efficient text embedding. Inputs: text: the input text for which you want to generate an embedding. This can be a single string or a list of strings. Model: the OpenAI embedding model to use. You can choose from various models like text embedding ADA002 or text embedding Babbage001, each offering different trade-offs in terms of performance and cost. Outputs: embeddings: a list of numerical vectors representing the input text. Each vector has a dimension determined by the chosen OpenAI embedding model. Steps: text preprocessing: the input text is cleaned and tokenized to prepare it for embedding. This might involve removing punctuation, converting text to lowercase, and splitting the text into individual words or sentences. Embedding generation: the prepared text is passed to the chosen OpenAI embedding model, which produces a numerical vector representation of the text. This vector captures the semantic meaning of the text in a high-dimensional space. Metrics: embedding similarity: the cosine similarity between two embeddings can be used to measure the semantic similarity between two pieces of text. Embedding quality: the quality of the embeddings can be evaluated by assessing their ability to capture semantic relationships and enable effective downstream tasks, like information retrieval, visualization plots, TSNE visualization. TSNE distributed stochastic neighbor embedding can be used to visualize the embeddings in a lower dimensional space, helping to understand the relationships between different text samples. UMAP visualization: uniform manifold approximation and projection. UMAP provides another method for dimensionality reduction and visualization, often producing more intuitive and informative plots than TSNE. Fine-tune parameters: model choosing the right OpenAI embedding model based on your specific needs, e.g. accuracy, cost, speed is crucial. Dimensionality: the dimension of the embedding vectors can influence the performance and computational cost of downstream tasks. Experimenting with different dimensions might be necessary to find the optimal balance. Uncertainty methods: non-OpenAI embeddings are deterministic, so no specific uncertainty methods are typically used. However, techniques like ensemble methods or dropout can be explored for quantifying the uncertainty in embedding generation. Challenges and fixes. Challenge 1: handling long text when dealing with long text inputs. The OpenAI embeddings API may have limitations on the maximum token count. Sample use case that resulted in challenge 1: attempting to generate an embedding for a long document exceeding the APIS token limit. Fixes to challenge 1: break down the long text into smaller chunks. Employ methods like summarization or sentence selection to reduce the text length before embedding. Challenge 2: resource constraints. Generating embeddings can be computationally expensive, especially for large text datasets or high-dimensional embedding models. Sample use case that resulted in challenge 2 generating embeddings for a massive corpus of text data. With limited computational resources, fixes to challenge 2 consider using a smaller embedding model for a trade-off between accuracy and efficiency. Utilize cloud-based services or distributed computing frameworks to handle large datasets efficiently. Explore methods like dimensionality reduction to reduce the computational load. Langchain Open AIs. Description: Langchain OpenAI LLMs provide a robust interface for interacting with OpenAI's powerful language models. LLMs like GPT-3, GPT-4, and others. These LLMs are known for their impressive natural language processing capabilities, enabling various applications like text generation, summarization, translation, question answering, and more. Langchain simplifies the integration of these LLMs into your projects by offering a structured and intuitive framework for handling prompts, responses, and model management. Inputs. Prompt the input text or question that you want the LLM to process. This is the core element that drives the LLM's response. Prompts can be simple or complex, and their structure significantly impacts the output. Model name specifies the OpenAI LLM you want to use, e.g. Text DaVinci 003, GPT-3.5 Turbo. Each model has unique strengths and limitations, influencing the quality and style of the generated response. Outputs. Response: the LLM's output, which can be text, code, summaries, translations, or any other format relevant to the prompt. The response is generated based on the input prompt and the selected LLM's capabilities. Metadata: additional information about the response, such as the model used, the response time, and other relevant data points. Metadata can help you understand the context of the LLM's output and assess its performance. Steps. Prompt construction: carefully craft a prompt that clearly expresses your request or question. A well-structured prompt is crucial for guiding the LLM towards generating the desired output. Model selection: choose the appropriate OpenAI LLM based on the task at hand and the desired level of accuracy and performance. Different models have different strengths, so selecting the right one is important. Response handling: process the LLM's response according to your needs. This might involve extracting specific information, analyzing the generated text, or further processing the output. Metrics. Response quality: assess the accuracy, relevance, and coherence of the LLM's generated response based on your expectations. Model performance: monitor metrics such as response time, resource consumption, and the overall efficiency of the LLM. Visualization plots. Response length distribution: visualize the distribution of response lengths generated by the LLM to understand the typical output size. Response time analysis: plot the response times for different prompts or model configurations to identify potential bottlenecks. Fine-tune parameters. Temperature controls the randomness of the generated text. A higher temperature leads to more creative and unexpected outputs, while a lower temperature produces more predictable and coherent responses. Top K limits the number of possible next tokens considered during text generation, influencing the diversity and focus of the generated text. Max tokens defines the maximum number of tokens the LLM can generate in a single response. This parameter helps control the length of the generated output. Uncertainty methods. Temperature sampling: introducing randomness into the model's prediction process to account for uncertainty. Top K sampling: limiting the number of possible next words considered, potentially reducing uncertainty by focusing on the most likely options. Challenges and fixes. Challenge 1: bias in generated responses. LLMs can exhibit biases based on the data they were trained on. Sample use case that resulted in challenge 1: a prompt asking for descriptions of different professions, consistently generating gender stereotypical descriptions. Fixes to challenge 1. Data augmentation include diverse and balanced datasets during training to mitigate biased representations. Prompt engineering: design prompts that explicitly address potential biases and encourage the model to generate unbiased responses. Post-processing: filter or modify biased outputs after generation to mitigate harmful stereotypes. Challenge 2: lack of factual accuracy. LLMs can sometimes generate incorrect or misleading information. Sample use case that resulted in challenge 2: a prompt asking for historical facts generating incorrect information about a historical event. Fixes to challenge 2. Fact verification: implement mechanisms to verify the accuracy of the generated responses against reliable sources. Prompt engineering: frame prompts that encourage the model to cite sources or provide evidence for its claims. Knowledge integration: integrate external knowledge sources or databases to enhance the model's factual accuracy. Challenge 3: ethical considerations. The potential misuse of LLMs raises ethical concerns about privacy, security, and responsible use. Sample use case that resulted in challenge 3: the generation of harmful or offensive content using the LLM. Fixes to challenge 3. Content moderation: develop robust mechanisms to detect and prevent the generation of harmful content. Responsible AI principles: adhere to ethical guidelines for AI development and deployment, emphasizing fairness, transparency, and accountability. User education: raise awareness about the responsible use of LLMs and the potential risks involved. Langchain OpenAI LLMs Azure Open AI. Description: Langchain's Azure Open AI class provides a convenient interface for using OpenAI's large language models LLMs through Azure OpenAI service. It leverages the Azure OpenAI service to access and utilize powerful language models like GPT-3, GPT-4, and others. This class simplifies the integration of these LLMs into various applications and projects, allowing developers to harness their capabilities for tasks like text generation, summarization, translation, and more. Inputs. Model name: the name of the Azure OpenAI deployment to use. This deployment should be created in your Azure OpenAI resource. API key: your Azure OpenAI API key. API version of the Azure OpenAI API to use. API base: the base URL for the Azure OpenAI API endpoint. Temperature: a value between 0 and 1 that controls the randomness of the output. Higher values result in more creative and unpredictable outputs. Top: a value between 0 and 1 that controls the diversity of the outputs. Max tokens: maximum number of tokens to generate in the response. Frequency penalty: a value that controls the probability of generating a specific token based on its frequency in the previous text. Presence penalty: a value that controls the probability of generating a specific token based on its presence in the previous text. Outputs. Text: the generated text from the Azure OpenAI LLM. Steps. Initialization: the Azure OpenAI object is initialized with the necessary parameters, such as the model name, API key, and API base URL. API call: the Azure OpenAI object uses the provided API key and base URL to send requests to the Azure OpenAI API. Text generation: the API response, which includes the generated text, is processed and returned. Metrics. Generation time: time taken to generate the text. Token usage, number of tokens used in the request and response. Model accuracy, evaluation of the generated text based on specific criteria or tasks. Visualization plots. Text generation output, visualization of the generated text, highlighting key elements or patterns. Fine-tune parameters. Training data, the dataset used for fine-tuning the LLM on specific tasks or domains. Learning rate at which the model's weights are adjusted during training. Epochs, number of passes through the training dataset. Batch size, number of training examples processed in each iteration. Uncertainty methods. Temperature sampling, using a higher temperature value to introduce randomness in the output. Top P sampling, controlling the diversity of the outputs by limiting the probability distribution of tokens. Challenges and fixes. Challenge 1, insufficient API key or permission. Sample use case that resulted in challenge 1 when using the Azure OpenAI LLM. You may encounter an error if the API key is invalid or does not have the necessary permissions. Fixes to challenge 1: ensure that you have a valid Azure OpenAI API key and that it has the correct permissions to access the desired model deployment. Challenge 2: network connectivity issues. Sample use case that resulted in challenge 2: issues with network connectivity can prevent successful communication with the Azure OpenAI API. Fixes to challenge 2: verify your network connection and ensure that you can connect to the Azure OpenAI API endpoint. Challenge 3: model availability. Sample use case that resulted in challenge 3: the desired Azure OpenAI model deployment may not be available or may be experiencing downtime. Fixes to challenge 3: check the status of the Azure OpenAI deployment and wait until it becomes available again. Challenge 4: incorrect model name. Sample use case that resulted in challenge 4: the model name parameter may be incorrectly specified, pointing to an unavailable or non-existent deployment. Fixes to challenge 4: verify that the model name parameter accurately reflects the name of a deployed Azure OpenAI model. Challenge 5: rate limiting. Sample use case that resulted in challenge 5: Azure OpenAI service might enforce rate limits on API requests to prevent abuse or excessive usage. Fixes to challenge 5: avoid excessive requests within a short period. Implement strategies like back-off mechanisms to handle rate limits. Challenge 6: quota exceeded. Sample use case that resulted in challenge 6: if you exceed the quota for your Azure OpenAI service, you might encounter an error preventing further API calls. Fixes to challenge 6: review and adjust your usage to stay within the allocated quota. Consider upgrading your Azure OpenAI service tier if necessary. Challenge 7: token limit exceeded. Sample use case that resulted in challenge 7: you might encounter an error when exceeding the maximum number of tokens allowed in a single API request. Fixes to challenge 7: break down your input text or adjust the max tokens parameter to avoid exceeding the token limit. Challenge 8: invalid input. Sample use case that resulted in challenge 8: providing incorrect or invalid input, such as malformed text or unsupported formats, can cause errors. Fixes to challenge 8: ensure that your input text is valid and complies with the Azure OpenAI API requirements. Challenge 9: unsupported model features. Sample use case that resulted in challenge 9: attempting to use features or functionalities that are not supported by the chosen Azure OpenAI model can lead to errors. Fixes to challenge 9: consult the Azure OpenAI documentation to understand the capabilities and limitations of the specific model you are using. Challenge 10: authentication issues. Sample use case that resulted in challenge 10: errors in authentication, such as incorrect API key or authorization headers, can prevent access to the Azure OpenAI API. Fixes to challenge 10 ensure that the API key is correct and properly set in the authentication. Headers of your requests. Langchain Open AI LLMS Base Open AI. Description: the Base Open AI class provides a foundational framework for interacting with OpenAI's API. Specifically the models for text generation and other language tasks. It acts as a building block for more specialized OpenAI LLM implementations. Inputs. Text: the input text string that serves as the prompt for the language model. Temperature controls the randomness of the generated text, with a higher value resulting in more creative and surprising outputs. Default value is 0.7. Max tokens sets the maximum number of tokens the language model can generate in response to a prompt. Top specifies a probability threshold for the model to sample from. It influences the diversity of the generated text. Top restricts the model's selection of tokens to the top k most likely choices, affecting the likelihood of encountering novel or unexpected outputs. Frequency penalty adjusts the model's tendency to repeat tokens seen in the input text. Higher values discourage repetition. Presence penalty influences the model's likelihood of using tokens that have already appeared in the input text. Higher values discourage the use of repeated tokens. Outputs. Text: the generated text output from the OpenAI model based on the provided input prompt. Token usage information about the number of tokens used in the input prompt and the response generated by the language model. Steps. The Base Open AI class establishes a connection to OpenAI's API using the provided API key. It packages the input text and other parameters, temperature, max tokens, etc., into a request structure that aligns with OpenAI's API requirements. It sends the request to the OpenAI API and receives the generated text response. Metrics. Perplexity measures the model's ability to predict the next word in a sequence. Lower perplexity indicates a better understanding of the language. Blue score evaluates the quality of machine-translated text by comparing it to human-translated. References. Visualization plots. Attention visualization plots the attention weights assigned by the model to different parts of the input text, highlighting the model's focus during text generation. Token frequency histogram visualizes the distribution of token usage in the generated text, identifying common and rare tokens. Fine-tune parameters. Model name specifies the specific OpenAI model to use for text generation, e.g. Text DaVinci 003. Temperature controls the randomness of the generated text, with a higher value resulting in more creative and surprising outputs. Max tokens sets the maximum number of tokens the language model can generate in response to a prompt. Uncertainty methods. Temperature scaling. Adjusting the temperature parameter allows for controlling the level of uncertainty and randomness in the model's outputs. Top K sampling. Selecting the top K most likely tokens for sampling introduces a controlled level of uncertainty by limiting the model's choice. Challenges and fixes. Challenge 1. Rate limiting. Reaching the API rate limits can result in errors and interruptions in service. Sample use case that resulted in challenge 1: making a large number of requests within a short period of time. Fixes to challenge 1. Implement a back-off mechanism to wait for a specified duration before retrying requests. Utilize a token bucket system to manage the rate of API requests. Challenge 2. Handling errors. OpenAI's API can return error responses for various reasons. Sample use case that resulted in challenge 2: incorrect API key, invalid input prompt, or exceeding resource limits. Fixes to challenge 2. Implement robust error handling mechanisms to gracefully recover from errors. Log errors to track issues and identify potential problems. Provide user-friendly error messages to guide users on resolving issues. Challenge 3. Contextual understanding. The model might struggle to maintain context over long sequences of text. Sample use case that resulted in challenge 3. Providing the model with a lengthy conversation history where it loses track of previous interactions. Fixes to challenge 3. Utilize techniques like memory augmentation to allow the model to store and retrieve relevant information from previous interactions. Employ context windowing mechanisms to focus the model on a specific portion of the input text. For better contextual understanding. Challenge 4. Bias and fairness. Language models can exhibit biases present in the data they were trained on. Sample use case that resulted in challenge 4. Generating text that perpetuates harmful stereotypes or reflects biases based on gender, race, or other factors. Fixes to challenge 4. Implement techniques for bias detection and mitigation to address potential biases in model outputs. Use carefully curated datasets that are diverse and representative of the desired target audience. Provide clear instructions and guidelines for model usage to avoid misuse and potential biases. Langchain OpenAI LLMs base OpenAI. Description. Explain in detail. The Langchain OpenAI LLM base class provides a foundational framework for interacting with OpenAI's large language models (LLMs) within the Langchain ecosystem. It acts as a core component, simplifying the integration of OpenAI models into various Langchain applications. Inputs. Input 1. Explain in detail text or prompt. This is the primary input to the LLM. It represents the text or prompt that the user wants the LLM to process. The input can be a question, a statement, a story, or any other form of textual information. Input 2. Explain in detail model name. The specific OpenAI model name that you want to use. Popular options include Text DaVinci 003, Text Curie 001, Text Babbage 001, and Text Ada 001. Each model has different strengths and weaknesses. Outputs. Output 1. Explain in detail generated text. The LLM's response to the input. It is the output generated by the model based on the provided prompt and its internal knowledge. This text can be in the form of answers, stories, summaries, code, translations, or any other type of text. Output 2. Explain in detail model metadata. Additional information about the LLM, including its name, version, and possibly other relevant details provided by the OpenAI API. Steps. Step 1. Explain in detail prompt processing. The input text or prompt is formatted and prepared for the LLM. This may involve tasks such as tokenization or pre-processing to make the prompt compatible with the LLM's internal workings. Step 2. Explain in detail. API call. Langchain sends the prepared prompt to the OpenAI API, which utilizes the selected model to generate the response. Metrics. Metric 1. Explain in detail token count. A metric reflecting the number of tokens, words, or subword units used in the input prompt and the generated output. This is relevant for understanding the computational cost of using the LLM. Metric 2. Explain in detail API latency. The time taken for the OpenAI API to process the request and return the response. This is important for gauging the model's response speed. Visualization plots. Visualization plot 1. Explain in detail prompt and response length. A plot visualizing the relationship between the length of the input prompt and the length of the generated output. This helps understand how the LLM's responses scale with the complexity of the prompt. Visualization plot 2. Explain in detail API latency distribution. A plot displaying the distribution of API latency over multiple requests. This provides insights into the consistency and variability of the model's response time. Fine-tune parameters. Parameter 1 explain in detail temperature controls the randomness of the LLM's output. A higher temperature closer to 1 leads to more creative and unexpected responses, while a lower temperature closer to 0 produces more predictable and consistent outputs. Parameter 2 explain in detail max tokens sets the maximum number of tokens that the LLM can generate in its response. This parameter helps limit the length of the output and control the computational cost. Uncertainty methods. Uncertainty method 1 explain in detail ensemble methods using multiple LLM models to generate responses and combining the results. This can help reduce uncertainty by leveraging the strengths of different models. Uncertainty method 2 explain in detail confidence scores. Some LLM APIs provide confidence scores for each generated token. These scores can be used to estimate the LLM's uncertainty in its responses. Challenges and fixes. Challenge 1 explain in detail API rate limiting. OpenAI APIs have limits on the number of requests that can be made in a given time period. This can be a challenge when using the LLM for high-volume applications. Sample use case that resulted in Challenge 1: a chatbot application receiving a large number of user requests. Fixes to Challenge 1: implement rate limiting strategies in your application code to avoid exceeding the API limits. Consider using a queue to manage incoming requests and release them at a controlled rate. Challenge 2 explain in detail context window limits. LLMs have a limited context window, meaning they can only remember a certain amount of past text. This can be a challenge when dealing with long conversations or complex tasks that require a longer memory. Sample use case that resulted in Challenge 2: a chatbot application that needs to remember past conversations to provide contextually relevant responses. Fixes to Challenge 2 utilize techniques like chunking to break down long text into smaller segments that fit within the LLM's context window. Consider using a specialized memory component in your Langchain application to store and retrieve context information.